Okay, let us recall our proof of Sperner's lemma and see what really went into the proof. So, we should try and analyze this a little bit more. So, the key observation or the first construction was to construct this skeleton, this red blue skeleton that we talked about, and the second thing was to realize that the skeleton was a graph, and the key property we used is that this skeleton has an odd number of edges which are sticking out of one side. So, this number is odd, and finally the fact we used was that the number of, so finally the other key fact we used is that the total sum of all the degrees of the vertices of a graph is an even number. So, as a consequence, the number of vertices with odd degree in a graph is always an even number. Okay. This follows from the fact that the sum of all the degrees put together, sum of all degrees is always even. It was twice the number of edges, and that implied this other fact. Okay, and this was what went into the proof of Sperner's lemma. Now, once we realized that that is basically all we used, what we should try and do is to see if we can somehow change the hypotheses of Sperner's lemma or modify it in such a way that we can prove something more or something different. Okay. So, often this is something that one always tries to do in mathematics. Just because we are given some set of hypotheses and we sort of know one way of proving what we want from those hypotheses, we usually do not stop there. So, we also often want to analyze the proof and understand how every part of the hypothesis was used in the proof itself. Okay, and doing that sometimes can help us prove a different statement or a stronger statement and so on. So, let us see how we can prove a slightly different statement. So, Sperner's lemma had the following hypothesis, that we have three different colors at the three vertices. So, we had blue, red and black, and then there was a condition which said that along each of the boundaries you had to put balls of either of the two colors of the two ends. So, either I put a red or a blue on this boundary. So, in this case I put both these blues and so on, and that was what led to this observation that when we draw the skeleton afterwards, the number of edges that stick out of the boundary was always an odd number, right. So, in this example there is only one of them. Let me make it slightly more interesting. So, let us imagine we also had a red ball here, then the edges of the skeleton. So, we have to look for a red blue, here is another red blue, here is another red blue. So, in each of these cases there would be an edge of the skeleton sticking out. So, you would get 3 edges. Now, since that is all we really need, what we could do is to modify the hypothesis. So, I do not really need to have maybe even a black on this, as long as when I look at the boundary, the total number of edges I see. So, here is black. So, I could even put black on this side. I guess I could put, let me say I could even put red on this guy. So, I will change the boundary conditions. So, the boundary I assumed had to have that particular feature, but suppose I start violating that, I allow for the boundary can have dots of any colors, okay, but subject to the following requirement, that the total number of red blue segments on the boundary should be an odd number. Okay. So, let us see if we have that in this example. So, here is a red blue segment. So, when I draw the skeleton I would get an edge here, here is another red blue segment. So, I would get another edge here when I draw the skeleton. Okay. So, I got 2 more and there were 3 to begin with. So, there is a total of 5 red blue edges on the boundary. So, the total number of edges sticking out is still an odd number now. Okay. So, I now say I allow for more general configurations of balls on the boundary, the new condition I want is that the total number of red blue segments on the boundary must be an odd number. If I have that, then the conclusion of Sperner's lemma still holds, because after that you just color the balls in the middle however you want. Okay, so I do this, suppose, then I claim that you will still be able to find an odd number of multicolor triangles. Okay. So let us see, so the balls in the interior I can color however I want. So let us try and see if we can find some multicolor triangles. So let us draw the skeleton in this case. So we have to look for the red blue edges. So here is one, here is a red blue edge, here is another red blue edge, okay, and now here is another one, here is another one, here is another one. So that is about it, right. So we can't find any more red blue edges in this figure. Okay, so if you recall, how did one look for multicolor triangles? There was an easy way of doing it. If one studied the skeleton, you just had to look for the edges whose which only have, or triangles which only have one edge leaving them. So let us find them here. So here is one multicolor triangle, because here is just a single edge which leaves it. So here is one of them. Okay, now here is another one, again for the same reason, that there is only a single edge. This again is only a single edge. This one here is not multicolor because it has got two edges, so we can say for sure it can't be multicolor. Here is another one. These all have two edges leaving them, so they can't be multicolor. And there is one more, which is this one here, and that is it. Okay. So you just have to look for the, you take this skeleton, it always becomes this funny shaped graph, and you sort of look for the ends of the skeleton, the vertices of degree 1, and those will exactly give you the multicolor triangles. Okay. So in this case we found 5, and again notice it is an odd number, and so let us be bold and make the corresponding theorem. So here is Sperner's lemma, if you wish, in a slightly more general format. So let us write this out. So let us call this Sperner's lemma version 2. So let us first recall what the original Sperner's lemma looked like. It said take an array of dots, color the three corners using three different colors, vertices along a boundary should have the same color as one of the endpoints, and so on. Instead, let me just delete these two intervening points, we do not need them anymore. Instead, we will just say color the boundary however you wish, subject only to the condition that there are an odd number of red blue segments. Okay, so let us take a triangular array of dots, and let me just say the following: color the dots using any of three colors, red, blue or black. Okay, so here the B is for blue. Now you just do it arbitrarily, but subject to the only condition that the boundary, which means all three of the segments of the triangle, the boundary should contain an odd number of red blue segments. Okay, so we sort of know what we mean by this. So one dot colored red and the adjacent dot colored blue. Okay, and this could be on any of the boundaries. So as we saw in these various examples, it could be like this, or it could be on the other boundary as well. Okay, and I can have blue first and then red, or red first and then blue, does not matter. So you need to have an odd number of red blue segments on the boundary, and then the interior vertices can just be arbitrarily colored. Okay. Now if you do this, then the conclusion of Sperner's lemma still holds. Okay, so then here is a theorem, then there exists an odd number of multicolor triangles. In particular, there is at least one of them. Okay, proof, same proof, there is no change. Proof as for Sperner's lemma version 1. Okay, so this is an example of something new that you get just by proof analysis. Now observe the let us just be a little bit more ambitious. So observe, there is nothing sacred about red and blue, right. We just said let us pick two of the colors and try to draw the skeleton using those two colors. But of course you could have picked red and black, for example, as your two favorite colors and only looked for those segments in order to draw the skeleton, in which case again the same proof would work, except now you just need to put the condition that the number of red black segments is odd. Likewise you could say the number of blue black segments is odd. Okay. So in fact there is sort of a further strengthening of this. The boundary should contain an odd number of either red blue or red black or blue black segments. Okay. So let us just tweak it right away. So red blue, red black or blue black. So at least one of these three must be, there should be an odd number of those. Okay, so that is maybe Sperner's lemma version 2.1 if you wish, just a mild strengthening of what we had before. Let us make another observation about Sperner's lemma and what went into the proof again. So observe, we took this special triangular array that we have, that you can see right there, but in a sense we never really used the fact that the array of dots that we have forms this very nice array of equilateral triangles and so on. We never really needed the fact that the triangles were equilateral, for example. So Sperner's lemma would also hold if the underlying triangle that we have is not necessarily equilateral, just some random triangle, and with the following sorts of subdivisions. So I could, instead of dividing them into many small triangles in the equilateral manner, I consider something like this. Okay, so here's a subdivision. So I drew some outer triangle and then a bunch of triangles inside, and now the goal is the following. Where do you place the balls? You place the balls at the various vertices. So now the objective is to try and place balls at these places, subject to any one of the conditions. You either look at version 1 or version 2 based on whatever one wants to look at, and the same thing. So let us look at the original version of Sperner's lemma. Now what we do is place say 3 different colored balls on the 3 vertices. The boundaries have to have, each boundary edge has to have one of the 2 colors. So maybe this is black and this black. So I could have more boundary edges as well if I wanted, more balls on the boundaries. And the balls on the inside are arbitrary. You can just place them whichever way you want. So we could place say blue, maybe red here. So this is another sort of situation that one can consider, and again the conclusion of Sperner's lemma holds, that as long as you place the balls on the boundary subject to whichever condition you want, say Sperner's lemma version 1, then you will always be able to find an odd number of multicolor triangles. So in this example the multicolor triangles are here, there is only one in this case. So that is the lone multicolor triangle. So it is always going to be there, it will always be an odd number. Now what is the proof? Well, proof is again the same thing. So if you notice what did we actually do when we constructed the skeleton? I mean, it was nice to have equilateral triangles and so on, but we could have just as well done the same thing with, you know, we could have just put you know, imagine putting some dots in the middle of each of these triangles and then drawing the same sort of skeleton. So you imagine drawing the skeleton. So of course you eventually only draw those lines of the skeleton which correspond to having, say, red blue or blue black or whatever edges. So this would sort of be the full skeleton of this coloring. So the you know, that still makes sense as long as you have some bunch of triangles in this sort of configuration, and then of course among these you will only keep the reduced skeleton is only things which cross, say, blue and red edges or blue black edges or whatever. So again, in essence the proof is the same, but the underlying configuration of triangles we have allowed it to be a bit more general. So this sort of way of dividing one big triangle into smaller triangles in this particular fashion is called a triangulation. And Sperner's lemma still holds even in this more general case. Okay. Sperner's lemma true is true for in the setting of triangulations. Okay, so I do not want to get further into what triangulations exactly mean and so on. In the equilateral case is of course very nice and you know, sort of very symmetric and beautiful, so it gives us a more intuitive sense of what is going on, but you can actually do it in more generality. So one other question that, you know, one usually asks when trying to you know, when you have a statement like Sperner's lemma, which is sort of an existence theorem. It says that once you put balls, you satisfy the required conditions, you will always be able to find at least one multicolor triangle. Okay, so that is an existence theorem, and often one is not satisfied just with that statement, because usually one is trying to, you know, actually find the triangle, or one is trying to write a computer program which, given a configuration of balls and colors, will tell you which one of the triangles is the multicolor one, or, you know, find one at least. So this sort of thing is called constructing the solution or trying to find the solution. So some sort of algorithm or such like is what one seeks. So how does one do that? So to truly appreciate the usefulness of having a constructive approach, consider the case when your underlying triangle is this very large one. So imagine in general, let us say you had a 1000 cross 1000 cross 1000 equilateral triangle here, and you put your balls at various locations and then you are trying to find the multicolor triangle. So it can be a very difficult task, for example, to achieve just visually or by hand, and what you want is some sort of you know, algorithm, systematic algorithm which will sort of scan through these balls and find the multicolor triangle. So this sort of construction of the solution is what we seek, and to do this what we do is to use the skeleton, because the skeleton actually did more than just prove for us the existence. It actually allowed us to say where the multicolor triangles lie. So recall the skeleton basically had this form. There were sort of an odd number of edges leading inwards. So here I have 1 2 3 4 5 edges leading inwards, and then after that I do not quite know what happens. So it is some strange thing that goes on beyond that point, and what I know is that edges which, you know, for example, if so my skeleton could look like this and so on. Now what I do know is that if any segment, you know, any path of the skeleton or any vertex of the skeleton has degree 1, meaning there is only one edge leading out of it, then that triangle will be definitely a multicolor triangle. So the triangle I am looking for is basically the triangle which corresponds to the edge of degree, any edge of degree 1 in the skeleton. So the question now translates to the following: suppose I give you this the coloring, I can form the skeleton from it, and then using the skeleton, how do I find the vertex of degree 1 in the skeleton. So, how do I traverse the graph, the skeleton, in order to find the vertex of degree 1. So, that is basically what the question translates to. So, here is the constructive algorithm. So, you just traverse the graph. So, the skeleton is actually a very nice graph in the sense, recall all edges are either of degree 1 or degree 2, there are only two possibilities. So, either there is an edge coming in and an edge going out, that is one possibility, or there is just an edge coming in and then it stops there, right. So, how do you traverse this graph? Well, you do the following. So, we sort of know there are some external nodes, okay, and like I said, there could be, it's an odd number of them, it could be some large odd number, right, there could be 1001 external nodes, for example. So, what we do is we start with, say, the first of them. So, you start with this node and you just follow the graph, by which we mean you follow an edge. So, you go down that edge, now you reach the next vertex. Now, if that vertex is of degree 2, that means there will be another edge leading out of that guy. So, you traverse that edge, okay. So, you travel along this, once you get there, if it is of degree 2, you will find another edge, you travel along that, you travel along the next one if you find another, and so on. So, every time you hit a vertex of degree 2, you keep traveling along that, okay. And doing this process may, however, bring you back to, bring you back outside the triangle. You may again land up at a external edge, okay. If that happens, you just go to the next external edge in the lot. It could so happen that you start at the first external edge, external vertex, and you maybe land up at the third one, okay. In which case you start at the next available external vertex, which could have been the second one. So, in this example, my next available external vertex is the third one. So, I do the same thing, I traverse this path till I find my every time I have a degree 2 vertex, I just keep going to the next vertex along that path. So, here again I come back here and then I am left with one more vertex. So, I try doing the same thing, I keep traveling along it, and well, in this particular case it so happens that when I got to some point, that vertex had degree 1. So, I stop, I cannot travel anymore, okay. And when that happens, that means I have found my multicolor triangle, right. This guy here is my multicolor triangle. So, the question is that, will this always work? Can I always do this, if I had, like I said, a very large triangle? So, the answer is yes, meaning what can fail when we try doing this algorithm. What could happen is you start at a vertex, you follow the path, you come back outside, you do not stop somewhere in the middle, you do not get stuck, you are able to keep moving, and it ends up that you are back outside the triangle. When that happens, of course, it is no good, you have not found a multicolor triangle. So, you travel, you follow another path, you come outside. Why can't this happen to the very last path as well? Why couldn't the same thing have happened? We travel and then when we get there, and then maybe I come back outside the triangle. The point is, this cannot happen because we know that the number of external vertices is always an odd number. So, when I have an odd number of them, it can't happen that every path goes in and then is also going to come out, because when I go in and come out, that accounts for an even number of vertices, that is 2 vertices right there. I pick the next one, if I go in and I come out, that means 2 more vertices are accounted for, and so on. So, every single vertex cannot be part of such a path which goes in and comes out. At least one vertex must go in and get stuck in the middle, okay. And when you get stuck, what you have done is you have found your multicolor triangle, okay. So, this is a sort of a traversal algorithm which one can actually program on a computer, and this sort of gives you a systematic way of finding at least one multicolor triangle, okay. So, this is a constructive algorithm for a multicolor triangle. So, here is one last question about Sperner's lemma and these configurations, which I will pose and allow you to think about it. So, these are related to what we might call an extremal configuration. So, the word extremal, so for example, in calculus and so on usually means a maximum or a minimum or sort of one end or the edge cases in some sense. So here is a question. We know that if you place balls according to the conditions of Sperner's lemma, say version 1, then you will find at least one multicolor triangle. Okay. Now the question is, can you find or can you arrange the balls in such a way that there is exactly one multicolor triangle? So can you find a way to arrange the balls of 3 colors? So I am talking about Sperner version 1 such that there is exactly one. Okay. And the question again is in in how many different ways can you do it? Can you think of various ways of various arrangements which will realize this particular fact that there is exactly one. Okay, that is an interesting question for you to think about, maybe something we will talk about during the tutorials and so on. So let us pose another question to which I do not know the answer myself at this point. What do you think is the largest number of multicolor triangles you can obtain? And what configuration will realize this maximum number?